3.7 Rates of change in the natural and social science. The difference quotient, delta y over delta x, is the average rate of change of y with respect to x over the interval x1 to x2, where delta x is equal to x2 minus x1, delta y is equal to y2 minus y1. The limit of this difference quotient as delta x approaching to 0 is the derivative of y with respect to x and can be interpreted as the instantaneous rate of change of y with respect to x. Using Leibniz notation, we can write it as dy dx. Whenever the function y equal to f of x has a specific interpretation in one of the signs, its derivative will have a specific interpretation as the rate of change. And today, we're going to focus on physics. If s equal to f of t is the position function of an object that's moving in a straight line, then the difference quotient, delta s over delta t, represents the average velocity over a time period, delta t. The change in position divided by the time elapsed represent the average velocity over a time period, delta t. And v equal to ds dt represents the instantaneous velocity, the rate of change of displacement with respect to time. The instantaneous rate of change of velocity with respect to time is acceleration, which is also the second derivative of the position function. In the following example, we're going to solve a problem involving the motion of an object. Example 1. A particle moves according to a law of motion s equal to f of t greater than or equal to 0, where t is measured in seconds and s in feet. This position function f of t is equal to tq minus 9t squared plus 24t. Find the velocity in feet per second at this time t. We know the velocity function is the derivative of the position function. So vt is equal to the first derivative of this position function with respect to time t, which is equal to 3t squared minus 18t plus 24, which is the derivative of this function with respect to t. Part B. What is the velocity in feet per second after 1 second? The velocity after 1 second means the instantaneous velocity when t equal to 1. That is v1. So we substitute t equal to 1 into the derivative of the position function. So we get f prime of 1 is equal to 9 feet per second. Let's see. When is the particle at rest? The particle is at rest when v of t is equal to 0. That is 3t squared minus 18t plus 24 equal to 0. Take out this common factor 3 and factor this. We get 3 times t minus 2 times t minus 4 equal to 0. And this is true when t equal to 2 or t equal to 4. The particle is at rest when t equal to 2, 4. When is the particle moving in the positive direction? If we define the positive direction to be to the right, then moving to the left will be the negative direction. when the particle is moving in the positive direction, the particle is moving this way, and the velocity will be positive. That is, when 3t squared minus 18t plus 24 is greater than 0, and factor this, we got 3 times t minus 2 times t minus 4 is greater than 0. We know that this expression here is equal to 0 when t equal to 2 or t equal to 4. So I draw a number line for t, and I label this two important number, 2 and 4. Those are the t-intercept. Notice that y equal to 3 times t minus 2 times t minus 4. The graph of it is a parabola and open up because the positive coefficient on the t-squared. So I draw a parabola, opens up, and passing this to t-intercept. Notice that above this t-axis, y is positive, here and here. We know this t-axis, y is negative from 2 to 4. So for this to be greater than 0, which means for y to be greater than 0, the corresponding parabola will be this part and this part. Those have the y coordinate to be positive. Then the corresponding t will be this part or this part. Notice that we are given that the time t is greater than or equal to 0. So the interval for the time t that satisfy this inequality will be this interval union this interval. So when you're asked to enter the answer here using interrotation, you can put down the interval, bracket 0, 2, parenthesis, union, parenthesis, 4, infinity, parenthesis. Or you can put a comma between these two intervals. Part E. Draw a diagram to illustrate the motion of the particle and use it to find the total distance in feet traveled during the first 6 seconds. Here's a diagram, not drawn to scale. Remember, from the result we got from A, B, C, D, we know that the position function is this, the velocity function is this one. The particle is at rest when t equals 2 or 4, and the particle is moving in the positive direction on this two interval over here. And here we draw a straight line, and this particle is moving along this straight line over here. The initial position over here is equal to 0, and the time here is equal to 0. Notice that we're going to define the positive direction to be going to the right, and going to the left will be the negative direction. When t is in the time interval from 0 to 2, the particle is moving in the positive direction. So we draw this arrow pointing to the positive direction. In this case, is pointing to the right. When time t equal to 2, we substitute 2 into t and got the position is equal to 20 feet. So s equal to 20. Notice that when time t equal to 2, the particle is at rest. So the velocity for the particle is going to be equal to 0 at this moment. So v equal to 0 when t equal to 2. Between the time 2 seconds to 4 seconds, the particle is going to move in the negative direction, which means in this case, moving to the left. So we make an arrow pointing to the left, which means the particle is pointing to the negative direction. When t equal to 4, substituting 4 into the position function, we got the position is equal to 16 feet. So S is equal to 16. Remember, at this time, when t equal to 4, the particle is at rest. So the velocity is equal to 0 at this moment. When t is greater than 4, the particle is moving in the positive direction, so the particle is moving to the right. Substituting t equal to 6, we got the position at that moment is 36 feet. So when t equals 6 seconds, the position S is equal to 36 feet over here. Now to find the total distance traveled during the first 6 seconds, we'll add up the distance over here. So from here to here, we have 20 feet. From here to here, we have 4 feet. From here to here, we have 20 feet. So the total distance traveled during the first 6 seconds will be 20 plus 4 plus 20, which is equal to 44 feet. Notice that to calculate the distance traveled from time t equal to 0 to time t equal to 2, we can take the absolute value of f2 minus f of 0, which is equal to 20. And to find the distance traveled from time t equal to 2 to t equal to 4 seconds, we take the absolute value of this ending position f of 4, subtracting this starting position f of 2, and it ends up to be 4. And the distance traveled from time t equal to 4 to time t equal to 6 is the absolute value of the difference of the two positions, and that's equal to 20. Part F. Find the acceleration in feet per square second at time t. We know that acceleration is the derivative of the velocity function. Remember from part A, we got the velocity function is equal to this. So we're going to differentiate this function with respect to time t to get the acceleration, which is equal to 60 minus 18 feet per square second. Now, to find the acceleration after 1 second, we just need to substitute 1 into t in this acceleration function. Substituting 1 into t, we got the acceleration is equal to negative 12 feet per square second. Part G. Graph the position, velocity, and acceleration functions for t greater than or equal to 0 and less than or equal to 6. We were given the position function over here, and we found the velocity function and the acceleration function. We are going to graph them using some graphing device. And we got the graph for the position function, the velocity function, and also the acceleration function. For time t greater than or equal to 0 and less than or equal to 6. Part H. When is the particle speeding up? The particle is speeding up when the velocity and the acceleration have the same sign. For example, if we define going to the right as the positive direction and going to the left as the negative direction, when this object is moving to the right, velocity will be positive. And if acceleration is also positive, which means it is also pointing to the right, then the particle is speeding up and going to this direction. If the velocity is negative, which means the object is moving to the left direction, And if the acceleration is also negative, which means the acceleration is also pointing to this same direction over here, then the object over here will be speeding up in this direction over here. So the particle is pushed in the same direction it is moving. From this diagram, we see that this is going to happen when t is greater than 2 and less than 3, and also when t is greater than 4. Because when t is greater than 2 and less than 3, the velocity is negative. It is below this t-axis, so the velocity is negative. And the acceleration is also below this t-axis, and it is negative also. So velocity and the acceleration have the same sign. So the particle is speeding up when t is greater than 2 and less than 3. Similarly, when t is greater than 4, the velocity is positive. The graph over here is above this t-axis. So velocity, it is positive. And the acceleration, the purple one over here, is also above this t-axis. So the acceleration is also positive when t is greater than 4. So the particle is speeding up on the interval 2 to 3, union this interval 4 to infinity. When is the particle slowing down? We see that when t is between 0 and 2 seconds, the velocity is t-axis, and it is positive. The acceleration is below this t-axis, and it is negative. Velocity and acceleration have opposite sign, so they're pointing to opposite direction, so the particle will be slowing down. Also, on this time interval from 3 to 4 seconds, the velocity is below this t-axis, it is negative. The acceleration is above this t-axis, it is positive. So they are pointing to different direction. So the particle is slowing down. The particle is slowing down on the interval from 0 to 2, union 3 to 4.